experience.
Jono, band practice.
Yeah, one sec, Kev. I just need to do my experience. Love grunge mechanics is totes wicked. A. Love grunge. But the maths is super hard and causing me stress. Course needs more theme park rides. Kev, is it RYD, Zed? Never fear, Jono. The hardest of the maths is past. Stay patient. It'll fall into place soon enough. I love grunge too, and there's always more room for theme park rides in the lectures. In fact, there's actually some coming up later, so let's get into it. We're going to change topics today, and for the last segment of my half of the course, we're going to deal with non-inertial reference frames, and in particular rotational motion, because that's where non-inertial frames become rather interesting. So today's lecture is going to be kind of short. I just want to lay some of the groundwork for non-inertial frames. I want to do, in the first half, linear frames quickly, because it's often not covered in mechanics courses. It's just assumed to be one of those easy things that people will just get, and I want to make sure I do it properly. And then we'll set up the pieces that we need for later on in rotational frames. Okay, so you'll remember way back in lecture 1, we introduced this concept of non-inertial reference frames. We basically said that a non-inertial reference frame is one where Newton's second law doesn't hold because that frame is accelerating in some way. Okay, and there's two common non-inertial reference frames. One is linearly accelerating frames. So there's no rotational component to the motion. It's just either speeding up or slowing down. And the other is a rotational reference frame, and there, because the system is rotating, there's an acceleration implicit in that rotational motion. Okay. So what I'm going to do in the first half is just deal with linearly accelerating frames, and what I'm going to do is look at essentially an inertial reference frame. And the funny thing with Taylor's book is that in the first chapter he gives S, S dash, S double dash, and then later on when he deals with inertial frames he starts to refer to S and S naught. Okay, so I'm going to switch over here to S naught being the inertial frame and S being the non-inertial frame. And what we're going to look at is basically having a non-inertial frame that's just linearly accelerating with an acceleration A relative to the inertial frame S naught, right? So let's just skip this down so everyone's clear. Our inertial frame is S naught. Non-inertial is S in this particular case. And one thing that we do really commonly in dealing with reference frames is normally in mechanics we refer to acceleration and velocity and position with lowercase letters. Here, when we deal with reference frames, in order to keep a way of distinguishing things, we use capital letters. Okay, so when I say this non-inertial frame has an acceleration A, I'm going to use a capital A for that, okay? And if there's a velocity, it'll be a capital V, okay? All right, so let's assume that we've got a situation that looks a little bit like this. There's a ball moving along with some velocity V, and you might be driving down the road in a car. So imagine we've got a vehicle here. It's traveling with, it's now a non-inertial frame, so I should probably circle this one. It's got some acceleration, and you might be trying to catch onto that ball as it flies past your window, okay? And it might seem a little bit of a contrived situation here, but what I'm trying to set this up is that the motion is in the same direction. So we've got an acceleration and a velocity this way, and our ball has a velocity this way, so that we don't have to get confused about which way the signs go, okay? Because you can imagine, you know, if you're accelerating like this, you'd want to catch the ball going the other way, but then we have to worry about which way the minus signs go. Okay, so if we consider the ball in our inertial frame S0, then because it's an inertial frame, we know that Newton's second law is going to hold, right? So our second law here basically says m r0 double dot is equal to F. Okay, so that's just Newton's second law, F equals ma, where I've written the position r0 in the frame S0, and I've got a double dot to tell me that's an acceleration, okay? All right. Now, if we go to the non-inertial frame, which is the one that we're interested in, we're going to describe the ball's position relative to S as R. And this will be because the two frames will have separate origins, right? We've got our inertial frame, which is stationary S0, and it will have some origin, and that origin is going to be fixed. And then our non-inertial frame, which is the one that's accelerating, its origin has to be moving with it, okay? Otherwise the positions are going to be changing as a function of time, and that's not very healthy to work out problems. And so we need a way to translate positions in the non-inertial frame back to positions in the inertial frame in the end, okay? That's all we're really doing. Okay. Now, we can think about this because the non-inertial frame is moving, and it's going to have some instantaneous velocity, right? Because it's got an acceleration, which means that its velocity is changing as a function of time. But at any particular point, what we can do is we can relate the velocity of the ball in the inertial frame S0 to the velocity of the ball in the non-inertial frame S, with an extra piece which is just the velocity of frame S with respect to frame S0, okay? And these velocities are basically just going to add vectorially. So what we can say in here is that R0 dot is equal to R dot plus V, okay? Where V is just the velocity of S0 relative to S, okay? So it's just the speed at that particular point in time that frame S is moving relative to S0, okay? So I've actually just got them back to front. And this is probably the most tricky bit. These are actually it's two most tricky bits of dealing with non-inertial frames. One is keeping track of which frame is which and making sure that you don't mess that up. And so that becomes less a hassle of trying to do really difficult maths and more just slowing yourself down enough to make sure you're keeping track of what's what. And the other one in here is a visualization challenge, is actually working out, does it make sense with what I would see in this particular scenario, okay? So let's think about this in words for a second. And I won't write it down because it'll take ages. If you've got my notes, I've got it written down there. Basically what we're saying here is that the ball's velocity relative to our inertial reference frame will be the velocity of the ball relative to the moving frame plus the velocity of the moving frame relative to the stationary frame, okay? And so let's think about this for a second. Imagine I'm in the non-inertial reference frame, and at a particular point in time I'm moving at 3 kilometers an hour forwards, and I look at the ball and the ball is moving forwards at 2 kilometers an hour. Then if I go back to my inertial reference frame, the velocity is going to be my 3 forward plus the 2 of the ball relative to me is going to be 5 kilometers an hour relative to the inertial frame, okay? So this adds up. Basically, the velocity in the inertial frame is going to be the velocity that's seen in the non-inertial frame plus the velocity of the frame relative to the other, okay? And in a lot of cases, it's really good when you're dealing with reference frames just to think through what what you've written means in words and whether that makes sense, okay? Most of the time you'll catch any mistakes that you make in there. There's one caveat I have to put in here, which is that if you're dealing with very high velocities close to the speed of light, in other words, you start talking about special relativity, this starts to break down a little bit, okay? Yvonne's going to teach that half. I'll let her get to it. And that's kind of why I want to set this up early, so that you're sort of thinking about what linearly accelerating frames do before you get to having to deal with them in special relativity, okay? All right, from here, things are not terribly difficult. We just have to do a little bit of maths because we've kind of got the visual aspect worked out. We can take our expression up here and we can differentiate it and just rearrange the terms, right? So if we take the time derivative, we're going to get r naught double dot is equal to r dot plus v dot. And of course, v dot is going to be a, and we can make r the subject. So this will now become r dot is equal to r naught double dot minus a, like so. And then we can multiply by m. So this will be now mr, I'm missing a dot just there, double dot, equals mr naught double dot minus ma. And of course, this mr naught double dot is just f, right? So this is f minus ma, like so, okay? And what I can say in here is that this is now the force that I would see on an object in my frame S, and it will be equal to the force that I would see in my frame S naught minus an extra term that is connected to the acceleration of the frame. And at first, this might seem a little bit weird, like I've got a force that's differing by an acceleration of a frame, what's going on here? But we all really actually know what this thing is, right? I'm sure you've all seen Top Gun before. If you watch in here, there, that is really what this minus ma term is, right? It's a little bit of an extreme example, but if you're driving in a car and you stomp on the accelerator pedal, you get pushed back into your seat, and there's an additional force component, and that force component is coming about because the reference frame that you're in, which is the car, is accelerating relative to the stationary reference frame, which is the outside. And that acceleration, big A, turns into a force, which is an inertial force in that system, okay? And likewise, if you stomp on the brakes or you do a carrier landing and catch the hook, then your stationary frame is, or your inertial reference frame is fixed. Your non-inertial reference frame is going from a velocity down to a lower velocity, so it's accelerating, but the acceleration is backwards now. And so there's going to be a minus ma, which will be a force acting forwards, which just sort of throws you forwards due to that acceleration. Okay, so we all know what this little term down here, ma minus ma, is. It's really just an inertial force. Okay, it's the force that comes about because you've got one reference frame accelerating relative to the other. Okay, fairly simple. And this is often why in mechanics courses people just skip over this, because they kind of assume, well, everyone knows this, it's not very hard, and they'll figure it out from the rotational frames. But I actually like to do it explicitly because it's actually really useful to see it done. So I'm going to do a quick example here, because sometimes you do actually see this turn up in problems. And so this is a problem that you sometimes call the accelerated pendulum problem. So consider a simple pendulum, mass little m, length big L, in a frame accelerated to the right with constant acceleration a. Find the angle phi equilibrium at which the pendulum will remain at rest, and the frequency of small angle oscillations about this equilibrium angle. Okay, So there's two ways you can imagine this. You can imagine this to be, if you're a carhoon, you might have a set of fluffy dice hanging from your mirror, and they swing backwards and forwards, and you put your foot to the floor, and all of a sudden you want to work out which way they're going to dangle backwards while you're screaming down the road. Or you could take our usual friend for pendulums, Professor Calculus from Tintin books, and stick him in a jet and fire the engines up and ask what happens, right? Might be a bit of a hair-raising experiment for him, given his excitable nature. So let's work our way through this problem, because it's actually a nice little one. And so we know, all of these non-inertial frame problems, usually the best way to begin is to think about what's going to happen in the inertial frame. So if we think about our inertial frame, we've got a pendulum. It's going to swing backwards and forwards. And there's two things we know. There's a force due to gravity, and there's a tension in the string or rod holding onto the bob at the bottom, okay? And what we're always going to do in this is play some game of balancing off the tension versus the versus gravity, such that if we go to some angle, then we have to do some decomposition into components, right? We always know this thing. And so the force here is just going to be the tension plus mg, which is our gravitational force. We don't even need to break this up into components. We're just expressing what the sum of the forces is in here, okay? If we now go to our non-inertial frame, there's now an additional force we need to account for, minus ma, which is our inertial force. And what we can do here is basically just add this onto the problem. So what I'm going to do is write mr double dot, just nice little notation change. Doesn't really matter what I write. I could put an F there if I wanted to as well. It's now going to be the tension that we had before plus our mg. And then what we're going to do is subtract an ma just in here, just to account for our change of frames, okay? And so if we wanted to, we could call this fs, and we could call this fs naught, for example, if you really want to. I don't do it in my notes because it's not really important to do it, but sometimes it's nice to keep track of these things. Okay, so one thing we notice in here is that the gravity component and the inertial force component are both connected to mass in here. So we can isolate that mass out. So this would become T plus mg minus big A, like so. And if we want to here, what we can do is basically combine that gravitational force to the accelerating frame in here. And so this thing would be T plus mg effective, where we call g effective equals g minus A, okay? Okay, all good. So what we're really doing here is basically just coming up with a combined gravitational force that builds in the gravity that we would have in an inertial frame plus some acceleration. So I always like to think about these in terms of flying planes. If imagine, and this is kind of a non-linear version, but it's hard to give you a good linear version for it. Imagine you're coming out the bottom of a loop. You've got gravity acting downwards plus the acceleration pushing you outwards while you come through the bottom of this loop, and so you would have greater than 1g coming through the bottom of that loop, and so that's why you get pushed down into your seat. And if you're on a commercial flight, you rarely get this sort of thing, but if you learn how to fly planes, you often do these sorts of trainings where you do unusual flight circumstances, and you can get, 2, 3G. If you're flying a jet plane, it's, upwards 9, 10, something like that. And you can do the opposite of that as well. So you can imagine going over the top, pushes you outwards, cancels out G, and you add this up. So you can imagine counting some effective G in here. And all we're really doing here now is going, okay, I've got my accelerating frame, I've got G pointing downwards. I've got an inertial force pointing backwards on me now. And if I imagine what's happening due to gravity, I'm going to have the vector sum of those. So I'm actually effectively going to have gravity pointing back that way. Okay? All right. And so we more or less have exactly this diagram up here. So what we've got is G pointing downwards. We add a minus A force to this, okay? So if you imagine our system here, it's accelerating forward. The inertial force is going to act backwards to that acceleration, so it's going to act in this direction towards the left here. And then our G effective is just going to be the vector sum, so it's going to be pointing back that direction. So we already know which way this pendulum is going to point at equilibrium. It's going to dangle backwards with an angle like the one just in here, okay? So what we've got here is G A or minus A, G effective, and little angle in here which we'll call phi EQ, and our phi EQ is just inverse tan of A on G. And I've chosen not to use G effective there just because it's a derived variable rather than a set variable, right? A is something big A is something I can set. It's just, you know, how fast I make the acceleration go. G is something that's kind of set by the mass of the Earth. It's not easy to change, but you could change it if you really put enough effort into it. And G effective is really just a sum of two things that would change, okay? So I'm sort of distinguishing my variables there, and it's often nice to write things in terms of things you can actually change. All right, and then the last part of this problem is to find the frequency of small oscillations about the equilibrium angle. I don't really want to go and... We haven't done that so far in this course, but you will have done it in first year. I don't want to go back and get it because it's kind of a bit of a trivial problem. So if you haven't seen this before, go back and have a look in your first year notes for it. The small angle oscillation frequency for a pendulum is omega equals square root G on L, and it looks very similar to the one that we have for simple harmonic motion, which is omega equals square root K over M. And so this is again why you learn it in first year, because you kind of have two parallels and you get two very similar equations out. You could pop these things out, okay? And this thing basically comes out in the case where, just in case you haven't seen it before, the angle is very, very small, so your sine theta component becomes roughly equal to theta, and you can take an approximation there to get this thing out, okay? The final answer here is actually really simple. What happens in here is we just have to replace G. And we replace G here with G effective. Just something on my notes, if I do a W slash, it's basically shorthand for with, and if I do a W slash O, it's shorthand for without. So we can come in here, and our omega here will be, let's make it clear that this is in the non-inertial, in the inertial frame, S naught up here, and in the non-inertial frame, WS down here. It will be G effective on L, and so this thing would be square root L G squared plus A squared just in here, okay? And of course, this G effective in here, we can get this by Pythagoras rule, right? So G effective up here is just going to be G squared plus A squared square root, okay? Or you could put some trig in there if you really wanted to as well, okay? Pretty simple, pretty straightforward. So what we're going to see if we basically did this, and you could do this experiment if you really wanted to. Unfortunately, our lab budget doesn't include a quarter mile of tarmac and a car with a really good engine to do your experiments in. Maybe you can put that in my experience that the university should increase our lab budget to enable such things. We once used to have a wind tunnel in the first year lab. There's a useful bit of trivia, a long, long time ago. But you can set yourself up and have a pendulum, and you can do your usual pendulum experiment, so count the number of things. And so you would take your car out, you would have, you know, a co-driver on the side who does the experiment, a driver who gets to... And you could put an accelerometer in the car and measure this thing, and you could actually go and work out, one, what the angle is. You could just have a camera set up and watch this thing, and the other one, what the oscillation period would be, and you'd have to have a kind of slightly more clever setup to do that, and you would be able to see this frequency change that you get due to acceleration in this. Okay, I'd love to have the budget to do it, but unfortunately I don't. So, got to live within reality, right? Okay, so let's take a break there, and in the second half I'm going to switch over to rotational reference frames.